right, this is part 2 of our Origin of Life set of notes. The first part ended on the 4 major ocean basins, so make sure that you have those: Pacific, Atlantic, Indian, and Arctic. So let's go ahead and start looking at these specific ocean basins and exactly their depth and their size. And we're also going to kind of look at our temperatures, and you can see all of this on our screen right now. We've got the Pacific Ocean, of course, being the largest and the deepest. So millions of kilometers squared, we've got 166.2, and our average depth in feet is about 13,741. Our temperature is going to depend on location for Pacific and Atlantic based off of the currents moving around, just because they are so large. Our Indian Ocean is the warmest, and our Arctic, of course, is the coldest. And we can kind of see these sea surface temperatures right here. If you notice, and in your head, you should go ahead and start thinking why it is so warm across that belt around the middle. So let's kind of talk about the difference between an ocean and a sea. So usually people kind of use these words interchangeably. We talk about the different seas, and we talk about the different oceans, so the Bering Sea, Pacific Ocean, but a lot of times, people kind of get them right just based off of looking at maps. We're going to kind of look at why exactly they're called an ocean and why exactly they're called a sea. So usually seas are smaller than oceans and are usually located where the land and ocean meet. So if you look, we've got our Bering Sea. We can see that, that's funny, we can see where the Bering Sea hits the Pacific Ocean, as well as hitting this eastern side of Russia and our western side of Alaska. So what we're going to kind of talk about now, since we've talked about the geology of Earth, we've talked about the formation of Earth, we're going to kind of look at the origin of life. And this is something that we look at from a scientific standpoint based off of evidence gathered from over many, many years of collection. So going back to our early atmosphere versus modern, and remember that the early atmosphere is an estimate based off of radioactive dating and collections from soil samples and other organisms. But we've got about 80% being water vapor, 10% being carbon dioxide, and about 10% being other gases. Whereas our modern atmosphere is a lot of nitrogen, about 78%. We've got a good amount of oxygen at 21%, and then our trace gases are going to fill in that last kind of 10%. So just take a minute, look at this graphic of our changing atmosphere over time. So we're looking at how the first atmosphere is forming from volcanic gas. Then we start getting our plants evolving in the oceans around 3,000, 2,500 a million years ago. Our oxygen is starting to build up in the oceans because of course, photosynthesis, as plants are starting to kind of produce that oxygen. And then our oxygen is going to kind of be released from our oceans and built up in our atmosphere, leading us to that 21% that we have about now. So in the 1920s and 30s, a lot of biochemical theories of how life originated on Earth kind of came about. Russian biochemist Alexander Oparin was one of these pioneers that kind of looked at all these different theories. And he started to hypothesize that life began in the oceans in the early Earth between 3.9 and 3.5 billion years ago, and that the first simpler organic molecules containing carbon formed as energy from the sun. And then this lightning and Earth's internal heat started to trigger chemical reactions to produce small organic molecules from substances present in the atmosphere. So we're starting to kind of bring all of this together. These molecules were kind of organized by chance into the complex organic molecules such as proteins, carbs, lipids, stuff like that, that are, of course, our basics of life. So our early atmosphere, initially water and carbon dioxide, we start getting this need for oxygen. So we start to think about where did it actually come from. And then Miller and Urey kind of came around with this idea of this primordial soup of the early oceans. These chemical reactions from inorganic compounds created this kind of abiogenesis of prokaryotes. And then these photosynthetic prokaryotes evolve, leading to oxygen in the atmosphere. And of course, life continues to evolve over several billion years. So let's look at this primordial soup theory, and we are going to kind of talk about this more in class and look at some different articles related to this. But we've got these inorganic compounds in the ocean, and they're starting to undergo these chemical reactions. These chemical reactions are starting to lead to the formation of these organic compounds, such as carbohydrates, lipids, nucleic acids, proteins. And all of these are going to lead to these basic cells, these prokaryotic cells. So this primordial soup theory is starting to state that chemicals in the atmosphere and oceans started to react in the presence of sunlight or lightning to make complex molecules that are the basics for life. Here are just some funny little cartoons to show you these different theories. All right, so then this multicellularity started to kind of evolve. So as early as 2 billion years ago, some cells stopped going their separate ways after replicating and started to actually evolve into having these specialized functions. So they started to give rise to Earth's first lineage of multicellular organisms, such as the 1.2 billion year old fossilized red algae you can see below. And we can see that it's kind of starting to take on this multicellular form. So this is a part of something that you do kind of need to know. These mixture of gases containing water vapor, methane, ammonia, hydrogen are being exposed to this UV radiation and lightning, starting to cause these chemical reactions and then producing these organic compounds. So this is an easy little way to kind of show this summary of the Miller-Urey theory. So let's go ahead and start looking at kind of the age of the Earth. So some of our oldest rocks we can date back to 3.8 billion years ago. This is the same age as our moon. So this is pretty great technology that we can use to kind of see exactly how old Earth is. And how exactly do we know this? So we're going through radiometric dating. So we're looking at these radioactive isotopes found in rocks, and they're starting to decay at these constant rates. So you can think about your half-life. So the older the rock, we've got more decay. As scientists started to kind of gain the technology to accurately, or as close to accurately, kind of age our rocks, they started coming up with this geologic time scale, and it's a record of the life forms and geologic events in Earth's history. So scientists started researching rock layers and fossils. They started doing radioactive dating. And we're going to start to kind of practice this radioactive dating. And this is very important to know in a scientific classroom, because all throughout high school and all throughout college, you're going to end up using this radioactive dating method. And of course, we are looking at the half-life. So on this word problem, I want you to go ahead and start to figure that out. Please pause the video here. So going back to this radioactive dating and calculating our half-life, suppose a rock has 10,000 parent atoms when it forms. Its half-life is 10 years. That means after 10 years, only half the atoms remain. So we're going to look at it in increments of 10 years. So after 10 years, we have half remaining, which of course is 5,000. After 20 years, we're going to have half of that, which is 2,500 parent atoms. At 30 years, we're going to be about 1,250 parent atoms. 30 years, we're about 625 parent atoms, and then 40 years old, we're looking at about 312.5 parent atoms. So let's go ahead and kind of look at how we divide the age of the Earth. So eras are divided into periods, and periods are subdivided into epochs. And a good way to remember this is era plus period equals an epoch. So we're starting to kind of look at the breakdown of that. The four eras, and you do need to know these, are the Precambrian, the Paleozoic, the Mesozoic, and the Cenozoic. And in the Precambrian, we've got about 88% of Earth's history happening in this time period. So 3.6 billion years ago to 544 million years ago is that Precambrian period, or era, sorry. Our Paleozoic era spanned from about 544 million years ago to 245, and this is where we start to see our ancient life. In our Mesozoic, we're going from 245 million to 65 million years ago, and this is kind of our middle life area. And our Cenozoic is our recent life, so this is spanning from 65 million years ago to present day. So with life in the Precambrian era, we're starting to see that this appearance of life in the fossil record is at nearly the same time that oceans start to appear on Earth. And life in all of Earth's history has had a strong and essential association with water. So this is why we are kind of in this class. We're studying why exactly it's so important to us. So where on Earth there is water, of course life can be found. In the Precambrian era, we're starting to see these archaebacteria. So they're starting to thrive in these extreme conditions, like down in the hydrothermal vents. We've also started seeing our sponges, our jellyfish, our anemones, our corals, and we've got our annelids, which are our segmented worms and tube worms. So in the end of the Paleozoic era, we got the Permian extinction. And eras are often ended by dramatic environmental changes resulting in these major extinction events. So it's not exactly yet known what event or events caused the Permian extinction, but 95% of all land species and 90% of all ocean species suffered extinction. So we can kind of attribute this to a combination of impact events. We can do volcanism, and a climate change is likely the culprit. So let's talk kind of about life in the Mesozoic era. So many different evolved forms of life started appearing after this Permian extinction. So this is likely due to the abundance of niches vacated by these extinct ancestors. So we end up with these jawed fish, aquatic reptiles, and coleophods. So we've got squid and ammonites, and they're starting to dominate these seas over the Mesozoic era. So at the end of the Mesozoic era, we're getting this impact event slightly in the region of the Yucatan region of Mexico. And we're thinking about this happening around 65 million years ago. And this may have set in motion a series of environmental changes that, of course, once again led to the extinction of many species.